This is a video walkthrough for AQA A-Level Chemistry Paper 3 from June 2017. So this first question relates to the calorimetry in a cup required practical. We're trying to measure the enthalpy change for anhydrous magnesium chloride absorbing water to become the hydrated salt, including its water of crystallization. So ask for a reason why the enthalpy change cannot be determined directly by calorimetry. So, and if you think about it, it would be completely impossible to just absorb the water of crystallization and not for some of the salt to actually dissolve itself and become hydrated fully. So you just need to put something about it being impossible to stop it from dissolving. So we're now being asked to calculate the enthalpy change for the absorption of water. Now they've given us enthalpies of solution, so if you remember your definitions, the enthalpy solution is it going from being a solid to being fully hydrated ions. And they've given that to us for both the magnesium chloride and the magnesium chloride with the water. So if we draw up a little enthalpy cycle and we have the reaction we want to measure across the top, and then both of those things, when they go through enthalpy solution, they turn into hydrated ions. So you'd end up with fully hydrated magnesium 2+ and fully hydrated 2 lots of chloride ions, so aqueous chloride ions. The 4 waters you don't have to worry about because they don't change. The 4 waters are they don't change, so the 4 waters would stay the same on all the sides. So if you look at adding up and putting in the values for the different arrows, so to go from magnesium chloride to the Mg2+ plus 2Cl- is -155. To go from the hydrated salt is -39, and then if we look that we're going the alternative route around the cycle rather than going the direct route, the indirect route, we can see we're going in the same direction as the -155 but in the opposite direction to the -39, which means it's going to be -155 minus, so plus 39. That's going to give us a final answer of -116 kilojoules per mole. So 1.3 is a 6-mark level of response question asking you about practical details and how you would do this experiment. So you need to think back and remember the calorimetry in a cup practical that you did back in year 12. So if you remember, this is where you have the polystyrene cup and you put the solution, you add your water or your solution, and then you carefully weigh out the solid, you add the solid to the cup and you stir it and you measure the temperature. And the important thing being that you plotted a graph of how the temperature changed. So you would plot it before you added, and then you would start plotting it as soon as you added the solid and plot it until you got a nice line showing a regular amount of cooling, so that you could extrapolate the line back to the point where you added it, and that way you would miss out on the inaccuracy of the fact that it would start cooling as soon as you'd added it and never reach its maximum temperature. As always with these questions, my top tip is to write it like an experimental method, because it means that you're going to get your marks for logical sequencing. So steps 1 is going to be to measure out a sensible amount of the distilled water. Important that it's distilled, and also important that you say how much you're going to use. So it could be anything from sort of 25, 50 up to 100, and named apparatus. So I'm here going to suggest that we use a pipette and that we transfer it to a polystyrene cup rather than a beaker. The polystyrene cup is there to make sure that we limit how much any heat loss to the surroundings. So we transfer it to a polystyrene cup with a lid. So the next step is going to be to put a thermometer through a hole in the lid in the top of the polystyrene cup. and to take regular readings from the thermometer of what the temperature is for a few minutes before we actually add any solid to the water. The next step is going to be to weigh out the 0.8 grams of anhydrous magnesium chloride. Doesn't matter exactly how you say you're going to weigh it out, it's more important that you put the detail in. So I'm here going to say that I use a weighing boat and that I weigh it in the weighing boat, and then later on I'm going to say that I'm going to re-weigh the weighing boat to take away the mass of the empty weighing boat from the mass so that I know exactly how much I've added. And that we then need to go on to say how we're going to add the solid to the distilled water and pop the lid back on and stir it rapidly. Now we've added the known amount of solid to the cup, we need to say how we're going to take regular temperature readings. That can be every 30 seconds, it can be every minute, until we're able to see a regular trend in the temperature change. We're then going to plot a graph of temperature against time so that we can extrapolate a line back to the point where the solid was added. Now we're going to use the graph to work out the difference between the temperature at the start, the initial temperature, and the maximum temperature that would have been reached at the point where the solid was added. Finally, we need to say how we would process the results. So what are we going to do with that temperature change from the graph? So we need to calculate the energy that's been transferred to the water using the equation Q equals mc delta T. Where m is the mass of water, c is the specific heat capacity of water, 4.18, and delta T is the change in the temperature. And then finally, once we've got the difference from the weighing boat and we know the exact amount transferred, we can work out the number of moles of solid that was transferred and therefore calculate the enthalpy change by doing Q divided by the number of moles. And obviously that would give you an answer in joules per mole, so you'd need to divide it by 1,000 to get it into kilojoules per mole. This question's about Gibbs free energy, but it's slightly different to ones you've seen before. They're giving you Gibbs free energy at different temperatures and asking you to use them to calculate the entropy change for the reaction. So if we remember first of all that delta G is equal to delta H minus T delta S, what we can see is if you plot delta G on the y-axis and the change in temperature on the x-axis, what you will find is you will form a y equals mx plus c relationship, so a straight line graph, where m, the gradient, is going to be equal to minus delta S. So now we need to plot those data points. I'm able to enlarge it nicely because I'm using my iPad, but I think you guys have a bigger piece of paper than me anyway. There is marks for accuracy of plotting them. You're allowed sort of within half a square, but you do need to make sure that you plot your data correctly. So we plot the points, and then we should be able to see that we get a nice straight line and draw a line of best fit. Okay, and then to work out the gradient, we draw a nice big triangle on underneath the line. And as always with gradient, we're doing the change in y divided by the change in x. Okay, so remembering that our scale is going to give us a gradient in kilojoules per mole divided by temperature, our gradient is going to therefore be kilojoules per mole per Kelvin, but the standard units for entropy are joules per Kelvin per mole, so we need to go from kilojoules to joules, so we're going to make sure that we times it by 1000. So question 2 is about sulfuric acid and how it reacts with both alkenes, alcohols and sodium halides. So it's quite a synoptic question in that it draws together some organic and some inorganic. Okay, so naming the mechanism for the reaction with an alkene. Mechanisms with alkenes always are electrophilic addition. Then it says to outline the mechanism, so draw it out. Doesn't matter that we're using conc sulfuric acid with propene, it's going to be the same standard mechanism you've learned for electrophilic addition. The difficult bit is remembering the formula for concentrated sulfuric acid and making sure you know how to draw that displayed formula. So it's definitely worth learning what sulfuric acid looks like. It's come up on a few questions before. So once we've drawn the propene and the sulfuric acid, we then need to draw on the curly arrow. So remember, we always draw from the electrons to the atoms. So the electrons in the double bond come down and attack the hydrogen, and then the bond between the hydrogen and the oxygen breaks and the electrons move on to the oxygen. Then draw what's resulting. So now it's really important here to remember which is going to be the product that results, so which carbocation is going to form, and we're far more likely to end up with the positive charge. To show the major product, the positive charge will be in the secondary position rather than the primary position because the secondary carbocation is more stable. Okay, so we show our intermediates at this point. So both of them, so we've got the O minus and then the carbocation. And then we need a final further curly arrow to show the lone pair on the oxygen that's negatively charged attacking the carbon at the carbocation at the positive charge. You don't actually need, you've got your 4 marks there, but just for completeness, I'm just going to draw what the final major product would be. So next you're asked to draw the structure of the minor product. So if the secondary carbocation is the more stable that gives the major product, then you're going to have a product formed from the primary carbocation as the less stable and therefore the minor product. So that would be with the sulfuric acid on the end carbon rather than the middle carbon. So more on the stability of those carbocations, we're being asked to explain why the product we've shown in 2.2 is the major product. So you need to talk about it being formed from the secondary carbocation, which is more stable. But for 2 marks, you need to explain why it's more stable. So it's important that you talk about the positive inductive effect of the multiple alkyl chains. And the more alkyl groups there are on a carbon, the more of a positive inductive effect. So the more they push the more they push electrons towards that carbon, which is known as the positive inductive effect, which stabilizes and means that the positive charge can be spread out further. So in 2.5, you're being asked about butan-2-ol reacting with constant sulfuric acid to form alkenes. So the best thing to do is quickly sketch butan-2-ol at the side so we can think about which 3 isomeric alkenes it's going to be able to form. The other thing this question is asking for is skeletal formulae, so make sure you put your answers as skeletal formulae. So if we think about where the OH and the H can be removed to form a double bond, this is one of the options. So this is but1-ene. And then if you think about how the double bond can then form in the middle position rather than on the end, we're going to end up with but2-ene. But it does tell us in the question that 2 of these alkenes are stereoisomers, which is our clue that we're going to have an EZ relationship. So we can have another version of but2-ene, but then you need to classify them as E and Z. So the first one I've drawn, where the 2 methyl groups are opposite each other, is E for entgegen, opposite, and the 2 where I've drawn them on the same side is Z but2-ene, where they are together, okay, on the same side. So in 2.6, you're told there's a byproduct of the reaction we've just looked at, and the molecular formula would be C4H8O. So you need to think about what that could be. So it's not an alkene, but a different kind of reaction that we can have with concentrated sulfuric acid. So again, I just sketch what could C4H8O look like based on what butan-2-ol was, and I'd be going for butanone. Okay, so it's got the right molecular formula. So butanone, you don't need to put in a 2 because obviously it being a ketone, the carbonyl group is always going to be on the second position. And the role of the sulfuric acid this time, if we've gone from an alcohol to a ketone, the sulfuric acid must be acting as an oxidizing agent. Okay, how we could separate this from the alcohol. So things to think about here is that a ketone would have a very different boiling point to an alcohol because it's got different intermolecular forces, which means that fractional distillation would be the best method of separation. Now moving on to inorganic chemistry and looking at the reactions of group 7 halides. So concentrated sulfuric acid reacting with sodium chloride. Remember, it would be an acid-base reaction and you get steamy fumes. But then when it reacts with solid sodium iodide, the iodide is a much better reducing agent, a much stronger reducing agent, so it's able to turn the concentrated sulfuric acid into a mixture of products. You would get iodine, sulfur, and hydrogen sulfide. If you want more information on this, there is another one of my YouTube videos that covers the reactions of the halides as reducing agents. So another question on required practicals, this one looking at how the synthesis and purification of an organic solid. We did a very similar practical in class where you carried out a reflux and then you've allowed your mixture to cool, you filtered it, you will have then done a recrystallization and then use melting point to check the purity of your sample. So first question is about what the purpose of the anti-bumping granules is for. So they prevent bumping, which means large bubbles which would cause the mixture to shoot out over the top of the flask, by providing a surface for small bubbles to form on. So it reduces the size of the bubbles by providing a surface. So then we're asked to show by calculation that an excess of sodium hydroxide is used. So really important here, show that you're working out how many moles of ethyl benzoate have been used. So it's given to you, they've given you a density and a volume. So you know 5 centimetres times the density will tell you what the mass is. So that would be 5.25 grams. And then they've given you the MR, so if you know the grams and you know the molecular mass, you can work out the number of moles. So grams divided by the MR will give you the number of moles. The sodium hydroxide is a little bit easier to check. You have been given it as a concentration and a volume. So if you know the concentration and you know the volume, you can work out the number of moles of sodium hydroxide used. So now we've got both numbers of moles. Because the reaction is 1 to 1, when we look at the equation at the top of the page, we can say that the sodium hydroxide is therefore in excess because there's more moles of it. So next you're asked why an excess of sodium hydroxide would be used. As always, you would use an excess of one reagent to ensure that all of the other reagent reacted. So to ensure that the reaction goes to completion, or to show so that all of the ester would be hydrolyzed. We don't want any of the starting material left. Okay, they use an electric heater rather than a Bunsen burner, as we encourage you to when you've done these practicals for us in the lab. That's because the organic compounds that they are using tend to be quite flammable, so it's very much a safety precaution to use an electric heater rather than a Bunsen burner. Next practical question is why you use reflux. So what's the purpose of reflux? I always think of reflux as that you can allow it to evaporate, condense, and then react again. So reflux allows the reactant vapour to condense and return to the flask so that it can continue to react. It's particularly useful for organic chemistry where you might be using quite volatile chemicals that evaporate at quite low boiling points. So the hydrochloric acid is added at the end to turn the salt back into benzoic acid. So the sodium benzoate is C6H5COO minus and then Na plus, or COONA. If we add that to HCl, then we end up with benzoic acid, so C6H5COOH plus NaCl salt. Okay. Now back to intermolecular forces. Why is sodium benzoate soluble in cold water but benzoic acid is insoluble in cold water? So sodium benzoate is ionic, and as I hope you're aware, ionic substances are pretty much always soluble. They're able to form ion dipole bonds with water because of the polarity of water molecules. Whereas the benzoic acid has the carboxylic acid group in it, and the carboxylic acid group is able to form hydrogen bonds, but it's attached to quite a large non-polar benzene ring, and that benzene ring, it's only got the one carboxylic acid on there, so the hydrogen bonds formed are not enough to make the benzene ring soluble. So because the benzene ring itself is very non-polar, you're not going to be able to surround the whole thing and hydrate it with water molecules, therefore it's going to be insoluble. So here's another 6 marks for a method. So describing the process of recrystallization. So important things to point. So state what the purpose of each step in the recrystallization is, as well as giving a logical sequence. So write out a method for how you would do the recrystallization. So first thing is going to be to dissolve the impure solid in a minimum amount of hot solvent. Okay, so the key thing being that you're using a solvent that it is able to dissolving when it's hot but not when it's cold. So by using a minimum amount, we're going to end up with quite a saturated solution. So we want to dissolve in a minimum amount of hot solvent. Okay. And then you're going to need to conduct a hot filtration, because any impurities that are insoluble will still be in the solution at this point, and you're going to want to do a filtration using a hot funnel and a warm piece of filter paper so that you can try and filter your solution while everything is still hot, so that you can take out any insoluble impurities. The next step would then be to allow the solution to cool, and you want that to happen quite slowly because you want some big crystals to form. So we allow it to cool and crystallize. Once it's crystallized, it's then important that it is filtered using vacuum filtration, so using reduced pressure, Buchner funnel and a Buchner flask connected up to a vacuum pump. And you do that so that you can filter it quite quickly, and this is to remove any soluble impurities. And then it's important that you wash your crystals using an ice cold version of the solvent. And then you can suck air through to dry the crystals, or you can transfer your piece of filter paper to an evaporating basin and leave it in a warmish oven to dry. So we're told in a similar experiment, using ethyl benzoate, producing benzoic acid, given some data, can we calculate the percentage yield? They tell you how many moles of ethyl benzoate went in at the start and how many grams of benzoic acid have been produced. So I just quickly jot down, we've got ethyl benzoate turning into benzoic acid. The MR of the ethyl benzoate is 150. If I just jot down benzoic acid structure at the side and quickly work out its MR, I can work out, so I've got 84 plus 6 plus the 32, so that's 122. Okay, so I know how many moles of ethyl benzoate I've started with, so that's 0.040, which is given to me in the question. And I can work out how many moles of benzoic acid have been produced, so 5.12 grams divided by the molar mass. And I can work out that that's 0.042 moles. So this is interesting, we've made more moles than we started with. So if we do the number of moles of the product divided by the number of moles of the reactant and times it by 100, we end up with a percentage yield of 105%. So suggest why it's not 100%. It's not that we've lost any during the process, we've actually ended up with more, and this would suggest that there's still some impurities in there. Perhaps it wasn't dried sufficiently. So could still have some water or some solvent on the benzoic acid crystals. So question 4 is about the required practical, where we looked at the different pH curves for titration. This one in particular is about sodium hydroxide being added to a weak acid. So the first question asks about what the pH range of a suitable indicator for this titration is. So you need to remember that you look for where the steep vertical line is. So a pH anywhere on this line would be suitable, so somewhere in the range of about 7 to 10, or I think it says 7 to 10.2 on the mark scheme. It then says give the expression for the acid dissociation constant of Hx. So this would be just like it is that we've learnt about for HA, but we're going to put an X minus everywhere where we would previously have put an A. So Hx, H plus, X minus on the top and Hx on the bottom. Just like all equilibrium constants, it is products over reactants. So now you're being asked to calculate the concentration of Hx in the original solution. So looking at the graph of the pH titration curve, you're looking at what volume of sodium hydroxide has been added at the point where it goes through the steep vertical line. And then at that point, we know 24 centimetres of sodium hydroxide has been introduced. So we know that the concentration 0.1 times the 24 over 1,000 is going to give us a number of moles of sodium hydroxide that have been added, so 0.0024 moles. And if we know how many moles of sodium hydroxide have been added, and we know they react 1 to 1 because it's a monoprotic weak acid, then we can say if we divide the number of moles by the volume, and we know it was 25.0 centimetres cubed, then we will end up with an answer of the concentration. So 0.0960 moles per decimetre cubed. So then we're asked to calculate what the pH of the solution of Hx was before anything was added, any sodium hydroxide was added. So what was the original pH? So if we just remind ourselves of that expression for Ka that we wrote on the previous page, and if we rearrange that to make H plus the object, then we can say that so H plus is going to be equal to the square root of Ka times Hx. Remember, we're saying that X minus and H plus are the same to use the square root. And then if we pop in the values for Ka and Hx, and we get a value for the concentration of the H plus, and then to turn that into a pH we need to do negative log to base 10 of the hydrogen ion concentration. Okay, it then asks you to calculate the pH of the solution when half of the acid has reacted. So for this you need to remember, or you can work it out, so at half neutralisation then something very special occurs because X minus will be equal to Hx. If you think about it, during the reaction Hx turns into X minus. At halfway through you're going to have an equal amount of X minus and Hx. So at this point, if X minus and Hx are cancelled in the expression, then Ka is going to be equal to H plus, and pKa is going to be equal to pH. So calculating the pH of the solution at this point, so we're going to do negative log to base 10 of Ka, and so that was 2.62 times 10 to the minus 5, and we get a pH at half neutralisation of 4.58. For the final part of the question, it then says to plot those data on the graph and to finish off the pH curve. So if we plot the first one, the original concentration at 2.8, And then half neutralisation, the volume at this point is going to be half the volume of NaOH added, so at 12. And then a nice thing to note, so we get a nice smooth curve through, but remember to get the mark, you need to show it being steeper at the start because of the little bit of buffering that happens. And that's just something you need to remember about when you're reacting a strong alkali with a weak acid. So now we're coming on to section B, which is the multiple choice section. So on paper 3, you will get 30 multiple choice questions. The whole paper is worth 90 marks, so there's 60 marks on the long answer section and 30 marks on the multiple choice. It's recommended that you spend half your time on section A and half your time on section B, because although the multiple choice are only worth 1 mark, some of them are quite involved in how much they take for you to be able to answer them. So question 5 asks about which compound has the highest boiling point. So you need to start thinking about the intermolecular forces. So I would quickly jot through each one. So A is going to have hydrogen bonds, it's an alcohol. B is only going to have permanent dipole, and actually C and D are also only going to have permanent dipole. So A is the answer because hydrogen bonds are the strongest type. Then if we look at question 6, which is again going to be about intermolecular forces, this time it's about the melting points, you need to remember to put these in order, what the formula for the different molecules are in their elemental state. So phosphorus is P4, sulfur is SA, chlorine is Cl2 and argon is Ar. So therefore P4 and SA are the other way round to what they would be in the periodic table. So C is going to be the correct answer. Sulfur is going to have the highest melting point. Then phosphorus, then chlorine, then argon. So question 7 is asking you about transition metals and which one is not a correct statement. So if you pop through them all, so they're all correct apart from C, which says that a ligand accepts a pair of electrons. So we know that a ligand actually donates a pair of electrons. So question 8 is about cracking. So I'm going through each line and highlighting the bits that are wrong. So we know thermal cracking is high pressure, high temperature and produces mainly alkenes. So neither A or B are correct. And we know that catalytic cracking happens with a slight pressure and a high temperature, so D is incorrect. Okay, question 9 is asking you to work out the concentration of the hydrogen ions, so you need to just jot down a little calculation. So if H plus is the square root of Ka times Ha, and then if we pop in Ka and we pop in the concentration, and then quickly square root it, we'll get an answer. So we end up with 5.02 times 10 to the minus 11, and then if we square root that, we get the answer B. So question 10 sticks with pH, but this time using Kw. So quick reminder, Kw is the concentration of the hydrogen ions times the concentration of the hydroxide ions. In the question, they've given you Kw and told you the concentration of the potassium hydroxide. Potassium hydroxide is KOH, so it's only monobasic. So a quick calculation, 1 times 10 to the minus 14 over 0.46 will give us the H plus, and then if we do negative log to base 10 of that, we get an answer, and the answer is B. So question 11 is reacting masses. It's what mass of carbon is formed. So if you look at, there's every 2 moles of propene, you get 6 moles of carbon. So if you've got 3 times 10 to the minus 3 moles of propene, you would expect to get 9 times 10 to the minus 3 moles of carbon. To then work out what mass that would be, we times it by the molar mass, so times it by 12. That's going to give us number of grams, but it wants an answer in milligrams, so 108 times 10 to the minus 3 grams, if we jot that down, is 0.108 grams. So if we multiply that by 1,000, we'll get an answer in milligrams, so 1.08 times 10 to the 2. So 12 is about infrared spectroscopy. Main thing to see here is this big peak at about 1750. And if you look on your data sheet, you'll see that that's due to a C double bond O. There's no OH bond on there, and you can check the other things on your data sheet. There's no bromo, so the answer is C, butanal. So question 13 is about which pair of compounds doesn't form a racemic mixture. I'd quickly jot them all down and check which ones actually form stereoisomers. So if you jot down what you get and check which ones have a chiral carbon with 4 different groups around it. So A definitely does, so would form a racemic mixture. B, when you see how the hydrogen cyanide would react, you get the hydroxynitrile. Again, if you remember to put the hydrogen in, there's 4 different groups on there. C, the alkene with the HCl. So jot down how it would add to the double bond and you'd end up with a stereoisomer. D, once you draw it, so you're going to end up with the HCN on there, the hydroxynitrile again, but because it's got 2 methyl groups, then we can recognise that D would not form a racemic mixture because it wouldn't actually form any stereoisomers. Question 14 shows you an organic synthesis steps, but it's actually about mechanisms, and if you go through each step and think about what kind of mechanism is involved, you should fairly quickly recognise that step B is the only one that's a nucleophilic substitution. So question 15 is about cisplatting, but it's asking which one is the stereoisomer of cisplatting. So A is actually cisplatting, and B would be transplatting. C and D not relevant at all because the NH2 is not the correct ligand. Question 16 is about Maxwell-Boltzmann distributions, and it asks you which letter represents the most probable energy at the higher temperature. So the line I've just highlighted would be the line at the higher temperature. And if you remember how the axes are labelled, it's number of particles and energy. So the most probable energy is going to be on the bottom, so that's going to be D. So question 17 asks about vanadium oxide being used as the catalyst in the contact process. So if we remind ourselves that the contact process, the main part of it is where sulfur dioxide is being transferred into sulfur trioxide. So if we then look and it's asking which one is vanadium being oxidised, so we know that B isn't happening in the contact process. And then if we look at the oxidation states in the different steps, so for A, we've got vanadium going from +5 to +4, so it's being reduced. And then if we look at C and D, we can see in D, again, it's going from +5 to +4, but in C, it's going from +4 to +5, and therefore in C, it is being oxidised. 18 shows a section of a polymer chain and asks which 2 monomers could have been used to produce it. There's no easy way around this. You just need to look at the different monomers and work out which ones could actually be involved and eliminate some of them. So if we look at A, so if I highlight the 2 different ones in different colours, and you can sort of see where each one is, so where I've highlighted it yellow, it's that monomer, and green is that monomer, and I can fill the entire of the polymer chain from those 2 polymers. If I then look at the other, so the answer is A, but just in case you try to work it out for the others, there's B, it doesn't work, it doesn't fit. If we look at C, again, you can try and make it fit, but it doesn't work. And then if we look at D, we'll find the same again. So you can make some of the monomers fit, but not all of them. 19 is another reacting masses calculation. So if you work out how many moles of hydrochloric acid are being reacted, so 50 over 1,000 times 1.68, and we'll get the number of moles. And then if you look at the equation, for every 2 moles of hydrochloric acid, there's going to be 1 mole of zinc. So we need to halve the number of moles to get the number of moles of the zinc. And then if we times that by the atomic mass, we get an answer in grams. But we have been asked to give an answer in milligrams. So 20 is about equilibrium. The forwards reaction is exothermic, and we're told that the temperature of the mixture is decreased, and then the mixture is allowed to reach a new equilibrium. And then it says which one of these options would be greater for the new equilibrium than for the original equilibrium. So if we go through the different options, okay, so if we decrease the temperature, it's going to favour the forwards reaction because it's exothermic. So then you're looking at which one of these would be greater if the forwards reaction's favoured. So we're not going to get an increased mole fraction of carbon dioxide or the partial pressure of chlorine, and the total pressure of the mixture isn't going to be greater, but the value of the equilibrium constant, Kp, would be greater. Now this is because the equilibrium constant is the concentration of the products divided by the reactants, and if you've increased the number of products, then the number on the top is bigger, therefore Kp is bigger. So 21 is checking your understanding of curly arrows in mechanisms. So it's not a familiar mechanism, but you would be able to work out what would happen. So I've kind of drawn on at the top where the logical sequence of where the electrons would move to give the final product. And then if you go through the steps, you can say, well, A is definitely in there, C is in there, D is in there, but B is not. So B is the step that is the incorrect curly arrow from the mechanism. So 22 is about pH curves. So if you think buffers are able to maintain a constant pH even with small additions of acid or alkali, and they contain equal amounts of HA and A, or they contain both HA and A minus. So if we look on the pH curve, in that straight line where B is, this is where it's acting as a buffer. So 23 is about alcohols. Which of these options couldn't be produced by the reduction of an aldehyde or ketone? So it's basically saying which one's tertiary. Again, it's a good idea at this point. Just find a place on the page, sketch out the different things. If you can't see it straight away, sometimes a little skeletal sketch can help you see it. So A looks like that. There's B. And then if we draw C, okay, 3-methyl butanol, and then pentanthreol. So by sketching them, I can see that B is the one that's tertiary. So 24 is about stereoisomerism again, so I would recommend quickly just drawing them and checking which ones are able to form stereoisomers. So A, if we draw it quickly, would be able to form EZ isomers. B, quickly draw it. Okay, so that would be able to form enantiomers, optical isomers. And if we draw C, yep, that would be able to form EZ isomers. And then if we quickly draw D, So D does not have a chiral carbon, so D is the one that can't form stereoisomers. So on 25, we're being asked which one can form a polymer without needing another reagent. So you've got to look at what's on either side of the monomer and check that it's got both parts that are needed to do a condensation polymer. So you're looking for it to have a carboxylic acid and an alcohol to be able to form a polyester, or a carboxylic acid and an acyl chloride. So if we go through the different molecules, so A has got an alcohol on both ends, that's not going to be able to work. B has got a carboxylic acid on both ends. C has got an alcohol and an acyl chloride. And D has got a chlorine and a carboxylic acid. Now, chlorine can't even do condensation reactions, so the answer is C. So we've now got a fairly simple concentration calculation. So if we can work out how many moles of lead chloride there are, if there's 1.08 grams and we know the MR, we can work out the number of moles. So grams divided by the molar mass. And then for every 1 mole of lead chloride, there would be 2 moles of chloride ions, because the formula is PbCl2. And we've also got to take into account that this is in 100 centimetres cubed, so our number of moles is in 100 centimetres cubed, and we need to know what it is in a decimetre cubed, because we want the concentration. So this next question is about rates, and it's given us a rate equation and said the rate was measured when the pH was 7. So if the pH is 7, then we can work out what the hydrogen ion concentration is. So that's going to be 10 to the minus 0.7. And then if we know what the concentration is, and we know that the only thing that changes is the sulfuric acid concentration, but the iodine and propanone remain unchanged, but the new rate of reaction is 1/4 of the original rate, then if we times the concentration by 0.25, then we know that the hydrogen ion concentration gives us a new pH, and that new pH would be 1.3. So question 28 is about PV equals nRT, and it looks like it's quite complicated until you actually look at it in more detail. So if we pop in that we know the pressure and we know the volume, so we can work out the number of moles. If we know the moles of the CO2, then we know the total moles must be the moles of the CO2 and the argon together. And therefore the mole fraction is going to be the moles of CO2 divided by the total moles. So question 29 is about carbon-13 NMR. Remember, every individual carbon that's in its own environment will have a peak in the carbon-13 spectrum. There's no symmetry in this molecule, so all of the carbons are considered to be in their own environments. So it would have a peak for every one of those carbons. So for question 30, you're asked what volume of water do you need to add to give the desired new concentration. So there's many ways of doing this, but I think the easiest way is to work out what fold dilution you're doing. So if we're going from 1 molar to 0.05, that would be a 20-fold dilution. So we want it to be 20 times weaker, or 20 times more dilute. So, and we've got 5 centimetres cubed to begin with, so 5 times 20 would be 100 in total. So because we're starting off with 5, 100, take away the 5 that you're starting off with, it's 95 centimetres cubed that get added. So in this one, you're asked that if a solution absorbs light of different wavelengths corresponding to different colours, what ion is most likely to be in the solution? So first step, go through and try and remember what colours they all are. So you should know that dichromate is orange because it goes from orange to green when it's used in the test. The iron 2+ is green, or tends to form pale green solutions. The iron 3+ tends to have a sort of rusty orangey browny colour, so red-orange, red-brown. And the copper 2+, hopefully you all remember, is blue. So when you look, if it's absorbing red, yellow and green, it must therefore be shown as transmit the complementary colour, which would be blue. For 32, it says if a reaction is exothermic and has a negative entropy change, which statement is correct? So let's just remind ourselves, delta G is delta H minus T delta S. So if we're saying that delta H is exothermic, so that means that's negative. And the entropy change is also negative. So we're ending up with a negative, take away the temperature times something negative. And for it to be feasible, delta G needs to be negative overall. So depending on the size of that temperature, we're doing a minus minus. So if you look through the options, the only one that works, so A and D are definitely wrong. But if it was above a certain temperature, if T was large, then you would be doing delta G would end up positive. But if the temperature is small, so if the temperature is low, then you would end up with delta G as negative, which means the reaction is feasible. So 33 is another reacting mass. First step is 5.7 times 10 to the minus 2 kilograms. Well, that's 57 grams. And we know the MR, so we can work out the number of moles of that are used. So that's 57 over 78.5, so that's 0.726 moles. And then it tells us that it's a 62% yield. So if we know how many moles we've got, we can work out what 62% of that would be to give us the number of moles of product we would be expecting. So 62% of 0.726 is 0.45. And that's a number of moles. Quickly work out the MR of the product as 120. And then if we do the number of moles times 120, we'll get the answer of 54 grams. So the final question, question 34, it tells us we've got a volume of oxygen and a volume of nitrogen, both at the same temperature and pressure, are placed in an evacuated flask with a given volume. And then it says, what is the pressure of the gas mixture in this flask at a given temperature? So it looks like it's a PV equals nRT question, but when you actually look at it in more detail, it's actually quite straightforward. So if we consider PV equals nRT, well, the N, the R and the T have all stayed the same in the second flask. The only thing that's really changed is the volume. and the pressure, which will change as a result of the volume changing. So the number of moles, doesn't matter how much oxygen and nitrogen there is, the number of moles stays the same. R always stays the same, and the temperature, the 298 Kelvin, has stayed the same. So we know that our, whatever the pressure was times the volume initially is going to be equal to the new pressure times the new volume, because N, R and T always stay the same. If you do physics, you might have learnt this as P1V1 equals P2V2, but if you don't do physics, don't worry about it. So yeah, we can work out what the original pressure and so from the original pressure and volume divided by the new volume is going to give us the new pressure. Okay, so the answer is C. And that's the end of this paper.